Hi guys, Larry Feldman again. In this lesson, we're going to talk about continuous interest compounding. In another lesson, we talked about non-continuous compounding, where n, which is the number of times interest is compounded per year, was a finite number. In other words, if you compounded annually, n was 1. If you compounded weekly, n was 52, etc. Here we're going to um, figure out what happens to this formula, a equals p times 1 plus r over n to the nt. What happens to this formula as n approaches infinity? And uh, another way of thinking about this is what happens as we compound every second or every millisecond or every nanosecond. What happens as we compound interest more and more frequently to the point where n approaches an infinite number of times per year? Well, there is actually a formula for this, and I'm going to derive that by letting, we're going to use a new variable. We're going to let m equal n over r, and this is the same thing as m over 1 equals n over r. All I did is I put 1 in the denominator here. And if we take the reciprocal of both sides, we get 1 over m equals r over n. Okay, we're going to need this equation. We're also going to cross multiply here, and we're going to get n equals rm. We're going to need this equation as well. So let's come up to this formula and use the new equations that we just derived. We get a equals p times 1 plus, well, we have r over n here, but we know that r over n is 1 over m. And nt, by using substitution for n, we get rmt, like that. Now, what we want to do next is just rewrite this in a slightly different way. 1 plus 1 over m to the m, and that's all to the RT. In other words, when you raise a power to a power, you multiply the exponents. So we get m times RT, which is the same thing that we have here. But I need to group this in this way for a reason. And the reason is that there's a constant called E. This is the Euler constant, or the natural base, and it is defined to be the limit as m approaches infinity of 1 plus 1 over m to the m. And you can see that this, at least this piece right here, is identical to the piece above it. And let's also come back here for a second. Hopefully this isn't too confusing, but as n approaches infinity, m approaches infinity. These are directly proportional, or they vary directly. So what we have is a case where as n approaches infinity, m approaches infinity, and I can do a substitution like this. I can write the p from up here in place of this entire binomial raised to m. I can use the constant e, and then I still have the RT as with the product being the exponent here. So this is the formula for continuous for continuous compounding. And I know some of this may be a little bit advanced, but don't worry too much about the derivation unless you have to. Um, but I'm going to be focusing more in this lesson on applications of the formula that we just derived right here. Oops. Right here. Okay, so with that done, let's get rid of all this. And let's do a few examples. In the first example, let's assume that Tim wants to invest $1,000 in an account earning 10% interest. So we have to write that in decimal form. And he wants to invest the money for 5 years, and the interest is compounded continuously. So all we do is we use the formula below, A equals, and we substitute the values into the formula, 1,000 times e to the RT. So this is 0.1, 0.1 times 5, which simplifies to 1,000 times e to the 0.5. Now, most scientific calculators have a button for e. It's an irrational number, which means that the digits go on forever, and there is never a pattern in the digits after the decimal point. It's roughly 2.71, and it is a very important constant that you'll probably be covering more extensively in advanced math classes. And with the knowledge that e is approximately 2.71, let me just use these squiggly lines here. Approximately 2.71 on your calculator. Since you have an E button, you probably want to use the E button. If you don't have an E button, then just use 2.71. And substituting in E or using the E button, we get an answer of $1,648.72 roughly. Again, this is an approximation. There may be some rounding error, but the important point is to notice that he started with 1,000, invested it for 5 years, subject to this interest rate, and the interest was compounded continuously, and he ended up with over $1,600. So now let's do another example. Let's say that we know we know the final amount that we want to reach is $9,000, and we want to find out how much we need to start with. If we're investing in an account with an interest rate or an annual interest rate of 6.5%, so that's 0.065 in decimal, and we're going to invest for 8 years. So again, we just substitute the values that we know into the formula. 9,000 equals P. So we don't know P, we're solving for it, so let's just use the variable. E to the RT. Let me clean this up a little bit. So that looks like that. Now we bring this down. 9,000 equals P times, and using your calculator, we find out that E to this power, actually let's do this in stages. P to the power of, and we want to take 0.065 times 8, which is 0.52, We get 9,000 equals P, and then using your calculator, e to the 0.52 is roughly 1.68. Divide both sides by 1.68. These cancel. We have the principal equals 9,000 divided by 1.68, which is $5,357 roughly. And again, there's going to be some round off error here, most likely. Or actually definitely in this case, because I didn't write anything after the decimal point. So the person starts with $5,357 roughly, invests it for 8 years in an account earning 6.5% annual interest, and eventually gets to $9,000. Okay, last example. Excuse me. Let's assume that somebody wants to triple their money. So the person wants to triple their money, and they know the interest rate is 4%, and they want to know how much time it would take in order to triple the principal. So in this case, all we really know is that the final amount is 3 times the initial amount. A equals 3P. So we substitute what we know into the formula. A is 3P. We still have P on this side, E to the R T, like that. We divide both sides by P, and we get 3 equals E to the 0.04 T. Now we have to take the natural log of both sides. The natural log of 3 is roughly 1.099, and utilizing the properties of logs, we can move this exponent to the front. We get natural log of E here. Natural log of E is 1. So we get 1.099 equals 0.04t. Dividing both sides by 0.04. Those cancel. And we get t equals roughly 27.5 years. So that's how you solve a problem like that. That's it for now, and I will see you next time. Thanks.